Here we are then at the halfway point of our tour through the solid code principles, and that brings us to the letter L, which stands for the Liskov Substitution Principle, or LSP, named after Barbara Liskov, who was a computer scientist at MIT in the States. And what the LSP tells us is that a derived class must be substitutable for its base class, which in more general terms means that if you have a base class reference or a base class pointer, you should be able to put into it an object of a derived class and nothing untoward, nothing unexpected should happen. And that's a bit vague when we say untoward or unexpected. Obviously, it's going to behave differently, otherwise what's the point of having the derived class? But it shouldn't behave in an unexpected way. That means it shouldn't do things like throw exceptions that it wouldn't have done for the base class, that sort of thing. In languages, strongly typed languages like C++, C#, and Java, it almost happens automatically because the rules about a base class reference referring to a derived class object are enforced by the language. But even so, they're not completely enforced by those languages, and unless we're a little bit careful, occasionally we can make mistakes. And the problem with these sorts of mistakes over inheritance is they tend to look absolutely fine as we start out, and it can be months or years down the line when we realise we made an early mistake in our inheritance model and that we need to do something about it. So let's take a look at an example of that. And what I've put together here is a very simple playing card program. So we can see here we've got a playing card class. I've declared an enum for the suits, clubs, diamonds, hearts and spades. And we've got some constants for the named ranks. So for most of them we just call them 2, 3, 4, 5, 6, but aces, jacks, kings and queens have those special values. We've got a constructor that takes those values, pops them into a rank and suit property that we've got declared down there. And then we've got a few other things which we'll come to as we need them. But most particularly, we've got a toString that just prints out the rank character, which we can see is either an A, a 2, or a TJQK for 10, Jack, Queen, King. And then a suit character, which is just using the Unicode values for the 4 suits. So that's our playing card. And then I've also got this hand class, and a hand is simply a list of playing cards, however many you like, depends on what game we're going to play. Again, we've got the ability to print out the hand, just a toString that loops through all the cards. And also, we've got a way of evaluating the score for the hand. And all the score for the hand is it adds up the scores for the individual playing cards. And at the moment, the score for an individual playing card is simply its rank. So an ace is worth 1, a 5 is worth 5, a jack is worth 11, a king is worth 13. That's all we're going to have. And of course, one of the things we might do with inheritance is make different types of playing cards have different ways of scoring, but we're not going to be looking at that today. And so if we look in our main program, we can see that what we've done here is created 5 playing cards, popped them into the hand, and then printed out the hand with the score. And if we run that up, then we can see that the score is 27. So that's 4 plus 13 is 17, plus 1 is 18, plus 7 is 25, plus 2 is 27. So perfectly good what we've got there. Now, the way we normally talk about inheritance is we use the phrase is a kind of. So we could say something like a manager is a kind of employee, or a helicopter is a kind of aircraft, or a jumbo jet is a kind of aircraft. And if that makes sense in plain English, that's certainly a good hint as to the fact that we've got inheritance. So if we consider our playing cards, we can think of a regular playing card. So like here, the 9 of clubs would just be a regular playing card. Or we can have a picture card, like say the Jack of Hearts. And we ask ourselves, well, can we say a picture card is a kind of playing card? That seems to make sense. So that looks like we've got a good candidate for inheritance. So let's program that up. So in our cards, we will simply add a new class, and we'll call that picture card. And then we're going to immediately derive our picture card from playing card, and that will instantly require us to have a new constructor. So we'll put in our constructor, and we'll say, just like in the playing card constructor, that can take a rank and a suit, and pass those straight down to the base class. So base, rank, comma, suit. And then another thing you'll notice we had in our playing card constructor, we have this assert rank, so that if the rank is not in the range ace through to king, we throw an exception saying we've got an invalid rank. We don't have to worry about the suit because the suit's restricted to being one of those 4 enums, but the rank could be any integer at all, and we only want it to be in the range ace through king, so that's what we've got there. And so what I can do for our picture card is again call that assert rank, but in this case we're going to pass in the range jack through to king because it's got a more restricted range that we have in there. And then another thing we need to do is, for there to be any purpose in having this picture card as a derived class, it has to do something beyond what the base class does. So although we've talked about the is a kind of relationship, really on its own that's not enough. We should really be formulating phrases like a manager is a kind of employee who additionally has a budget or something like that. So we're saying that a manager has all of the features, all of the methods, all of the fields of an employee, plus they've got some other features of their own. And so here we need, in order for there to be any reason for this, we need to say a picture card has some other feature. And what I'm going to do is we're going to say that a picture card, because it represents a jack or a king or a queen, has a gender of male or female. So let's add an enum for gender. So public enum gender, and we'll just at the moment set that to F or M. And then we can put in our property of type gender called gender. And then all that needs to do is to say that if rank equals queen, then we want to return gender.female, otherwise gender.male. And then for that to make any sense, we're also going to want to put in a toString. So let's do an override of toString. And at this point, we hit one of the more subtle rules that we get when we're thinking about Liskov substitutability, which is the fact that not as an absolute rule, but as a piece of advice, a derived class method that's overriding a base class method should always do what the base class method does and then something additional. So just like we said with inheritance generally, you've got to do everything the base class does plus have other features. Same tends to go for when we're doing overriding. So what we're going to do here, for example, is we're going to return the base toString, which remember just displayed the rank and suit, and then we're going to add on the gender. So pretty simple here. We can just say we're going to return base.toString followed by gender, and that will just give us an MRF on the end. Now I said this idea that a overridden method should always do what the base class does plus something else is a piece of advice, because there are certainly circumstances when that doesn't make sense. The most obvious one actually is already here. In playing card, we do not want to call playing card's base class. So even though we've got an override there, because playing card, although there's nothing listed, is automatically derived from object. But we don't want to do that. If we were to in here put base.toString, then when we run that up, we'd see that on every one of them, the base toString just gives us the fully qualified name of the class, which isn't what we want at all. So in that case, it makes perfect sense not to call your base class method. So it's a rule that's not absolute, but whenever you're writing an override, I would default to calling the base class method and only not do that if you've got a really good reason, as we saw there. So having done that, let's now go back to our program, and simply where we've got that king of clubs, we know that that's not a playing card anymore. That should be a picture card. So we'll put that in there. And then when we run up the code, we can see that our king of clubs has now got the M over in the end of it for male. And if we had a queen, then that would have F for female. So we've introduced inheritance. We've introduced some slight change. And so far, everything seems to be going pretty well. Because C# is a strongly typed language, it's obeying the rules for us that when we've got a playing card reference here, PC2, we're allowed to put a derived class in it, whereas we wouldn't be allowed to put something totally unrelated in there. So I can't say something like playing card PC6 equals new overflow exception, because there's no inheritance relationship between those, and so the compiler is helping us out. But we have got a few problems here already. Because let's just take a look at what we've got here. Remember, in our playing card constructor, we had this assert rank that was saying rank has to be in the range ace through to king. And then in our picture card, we'd said that rank has to be in the range jack through to king, which seems perfectly okay. The intent of that is so that if in our program we were to try and create, say, a picture card outside the range, so if we said var pick equals new picture card, and then tried to put, say, a 7 of whatever suit in there, then when we run that, that's going to throw an exception saying argument out of range, we're not allowed that rank. But we actually haven't been thorough enough here, because at the moment what we could do is we could say something like var card equals new playing card, and then have a playing card that was the king of diamonds. Now logically that should be impossible, because playing cards are only allowed the range ace through to 10. If it's a king, it should be a picture card. But if we run that up, we see, no, that's working perfectly okay. It's allowed us to have a playing card that was the king of diamonds. And we can see what's gone wrong there. Although we've put the further restriction on picture card, that it's jack through to king, we've still said that playing cards are ace through to king, whereas in fact they're not. Playing cards are now ace through to 10. And so that should mean that now, when we try to create our king of diamonds as a playing card, let's just comment those out, then that should throw an exception saying that it was out of range, which is good. But if we try and then fix that, we can see that although that should work, it's also giving an exception. It's saying we've got an invalid rank of 13. And the problem is that's not an invalid rank for a picture card, because that's king, but it is now an invalid rank for playing card, because that's now been restricted to having the range ace through to 10. And a picture card is a kind of playing card, and therefore it must obey all the rules of a playing card. So we've got a bit of a problem here. Very, very quickly, we've discovered that what we thought was good inheritance, that a picture card is a kind of playing card, is actually starting to cause problems. Let's just set that back to what we had before for now, because I'll show you another problem that we have here as well. We've said that the Liskov substitution principle can be formulated with the idea that a derived class is a kind of base class. So here we've said a picture card is a kind of playing card. And then we said also that you then add features. So a picture card is a kind of playing card, plus it has a gender in our case. And we said that, for example, a manager is a kind of employee, plus they have a budget. But what you mustn't do, and this I find is really the best thing to bear in mind when you're trying to obey the Liskov substitution principle, you must never say something like a manager is a kind of employee except that they don't. So if you find yourself trying to say a manager is a kind of employee except that they don't earn overtime or whatever it may be, then you're going to hit a problem. And so let's have a look at an example of this here. What I've got in the program, if we just take that back to where it was, is this little function called display pips. And the idea of this is it's a function that will display on a playing card the pips that we have. So we can see that an 8, whatever suit it is, has that basic layout of 3 and 2 and 3, whereas say a 6 just has 3 and 3. And so I don't need to go into the details of this, it's a bit complicated, but basically we take in this tuple for what's going to be in each column. So if I wanted to say, do something like this, I could do a display pips, and then in there, let's have, say, the display for a 7, which goes 3, 1, 3. And then if we run that up, you can see it's defaulted to diamonds. We've got that fairly neat layout for how a 7 of diamonds is going to look. So in order to make that work, what I need to do is write a function on our playing card to get that tuplet for what the pip should look like. So what I'll do here is I will say we're going to have a public and then the tuplet, which is int, comma, int, comma, int, and we'll call this pip layout. And then, although there's probably a number of ways that we can do this, I'm going to do it pretty simply. I'm just going to say return and then use the new switch expression that we get in C#8, and I'm going to say something like ace gives and then 0, 1, 0, so we just got one of them on an ace, and then if we just copy a few of those, so 2, 3, 4, 5, 6, 7, 8, 9, 10, then we can just fill those in. So with a 2 we have 2 down the middle, a 3 we have 3 down the middle, a 4 we have 2 down each side, 5 is 2, 1, 2. You'll notice there's actually a bit of redundancy in here in that the two outer ones are always the same. So I could have cut that down, but actually I think it's a bit clearer if we leave it like this. 8 is 3, 2, 3. 9 is 4, 1, 4. A 10 is 4, 2, 4. And then we just put in the default. Anything else, we'll throw a new invalid operation exception, rank out of range. And then if we go back to our program, what I can do here is, let's have another static method, display card, and then we'll put a playing card in here, and then simply call display pips and pass in the card dot pip layout, and then also the card dot suit character. And also, just so we can see what's going on, let's do a console write of card itself, so we'll get the toString there. And then down here, I'll just say display card PC1. And then for variety, let's put 7 of spades in there, so that'll be PC4. And so when we run that, we can see we get the 2x2 pips for the 4, and then we get that structure for the 7, which is pretty much what you'd be getting if you looked at a deck of cards. But of course, what I deliberately avoided doing was saying we were going to have a display card for PC2, because PC2 is a picture card, and that throws an exception. That's the out of range exception that I put deliberately in there, because only regular playing cards can have this idea of a pip layout. When you've got a picture card, it's going to have an image, not a simple pip layout. So what's happened there is that's another breach of the Liskov substitution principle. I'm saying that a picture card is a kind of playing card, except that it doesn't have a pip layout. And although I've kind of forced that in there, that is typically the sort of thing that happens. Ways we get around it, maybe we, in that case, just return something like, say, the default is 0, 1, 0. But now when we run that, we get the fact that a king looks like an ace. That is going to confuse people and cause problems further down the line. So we've breached the Liskov substitution principle, and that's not what we want to do. If we consider this in diagrammatic terms, if we just take a look at a UML diagram here, this is the sort of situation we've got. We've got our base class playing card, and we've got our derived class picture card. And then once we've established a class hierarchy, we can then start adding new features and deciding where they go. So if we decide we want the idea of a rank, well, that's pretty obvious. We want a rank to go into our playing card, because all cards, playing cards and picture cards, have a rank, and the same would also go for a suit. Then we come along with the idea of the gender, and we said, well, only picture cards have a gender, so we put that in there on our picture card, and again, that's perfectly okay. But then we hit the problem, because now we want to say, what about this pip layout? Pip layout is something that we do have in a playing card, so we're tempted to put it in there, but something we don't have in a picture card, which means we have to remove it. And that's where we've breached the Liskov substitution principle. Another way of looking at that, actually, is it's also a breach of the single responsibility principle, going back to the first of our solid principles. Because if you think about playing card just as a class, our playing card class is actually attempting to do two things. Playing card is acting as a base class from which we can derive things like picture card, but playing card is also a concrete class from which we can create actual playing card objects. And that is two responsibilities, and we've seen pretty quickly they come into a conflict. So actually, that's a breach of the SRP. And if we want to fix that, then we should be designing our class structures in such a way that every class that we write is either a base class or a concrete class, but never both. So actually, we should be restructuring our code to look a bit more like this. So what I'm going to do is rename this one to playing card base, just to make sure it's clear what's going on. And then I'm going to add another class, and this one I will call number card. So a number card represents ace through to 10, and in that one, that's where I can give this the pip layout. And then I simply need to derive that from our playing card base. Tidy up the layout a bit. And there we have the structure that we want. So we've got an abstract base class, playing card base. We've got a couple of concrete classes, number card and picture card. And this is typically what you'll see in terms of the basic shape of your inheritance hierarchy if you're following this kind of approach. So often you'll see really quite long, deep inheritance hierarchies, whereas here we've got a shallow but broad one. And if we want to add new classes, we're just going to be adding new concrete classes along the way. So let's implement that in our code. So the first thing we need to do is take what was our playing card and rename that to playing card base. And then just let Visual Studio do the renaming of that universally. And then if we take a look at that, the first thing we need to do is make it abstract. So it's now an abstract base class. In the range, that's still okay, because given this is covering all playing cards, that's going to have the range ace through king. And then also things like the rank and the suit and the two string, they're all okay. The thing we're going to have to remove, I'll wait till I've got somewhere to put it, but is going to be the pip layout. So let's add that other card. So we'll add our class number card. And the first thing I'm going to do is derive that from our playing card base. That's got to have a constructor, so let's copy that from the picture card and just rename it to number card. But then, of course, the range here, this is where the range should be ace through to 10. So we've seen that the base class can have the complete range ace through to king. Our picture card has the range jack through to king, and our number card has the range ace through to 10. So that's that problem solved. We've now got consistency over all of those things. We also, as we said, need to take that pip layout, cut that out of there, and put it into our number card. And so now we can see we've got a much better structure. Our playing card base, as we saw in the diagram, just has the things that are common to all playing cards. So rank and suit, and then two string and a few things related to that. Our picture card derives from that and then just adds on the features for a picture card, which is gender. And then our number card, again, derives from the base class and just adds on the thing for a number card, which was our pip layout in the diagram. Then what else do we need to do? Well, if we go to our program, we'll see it's been a bit overzealous with its rename. So those should actually be now number cards. So let's pop that in. So in all of those. So we've got playing card base as the reference, but then we can put in either number cards or picture cards. Our hand, we should see again the rename did that, so that's just dealing with playing card bases, so that all works in the same way. But if we look up here, we can see now the compiler has done for us what previously was being a runtime error. We're not going to get an exception thrown now on pip layout. The compiler is simply going to say we're not allowed to have a pip layout because playing card bases don't have a pip layout. So either we could cut that all together, but in fact what we want to do is just say this function only applies to number cards. But again, it's the compiler making it work for us. So now, having done that, we've got to make sure the compiler knows these really are number cards. So actually, if we just put that on there as well, then that will work perfectly happily, and the program now works in the same way that it did before. So that's the way to get your code to comply with the Liskov substitution principle. Make sure that every class you write, you know whether its intent is to be a base class, in which case make it abstract, or whether it's to be a concrete class. We still have a slight problem in that although we're saying number and picture card are not supposed to have further derivations from them, it's still possible to do that. We could still write a derived class. The way to do that in C# is simply to declare these classes as sealed. So in Java and C++, that will be final, but in here we do that as sealed, and that will mean that no one's allowed to further derive. So if I were to just in here try and say class sum card colon number card, then we immediately get an error there saying that it can't be derived from a sealed type. That's quite a strict thing to do, and I have to say it's not something I'll always do when I'm programming, but as a general principle, whenever you write a class, you should really either be making it an abstract class or making it a sealed class. If you just leave them both off, then you're risking breaches of the Liskov substitution principle. So there we have it, the LSP. We've seen how it can be most simply put as saying when we do inheritance, we talk about the is a kind of relationship. So a derived class is a kind of base class, plus it can do other things as well. But what we must never do is say the derived class is a kind of base class, except that it can't do this. Although you may sometimes get that to work to begin with, you pretty soon hit the buffers. And we've seen that structurally, the easiest way to avoid that is to make sure that you're aware whether your class is a base class or a concrete class. If it's a base class, declare it as abstract. If it's a concrete class, declare it as sealed, but don't mix the two together. Next time, we're going to be looking at the interface segregation principle. But for now, hope you enjoyed that, and do remember to subscribe.